In the depths of the unknown, amidst mysteries that have stirred humanity's minds for centuries, lie questions that demand answers. How did we come into this world? Are we alone in the universe? What are the laws governing its boundless expanse? These profound inquiries greet visitors to the official portal of the James Webb Space Telescope, JWST, Observatory, inviting them on an extraordinary journey to the origins of existence. These fundamental enigmas, of course, are not new. They captivated thinkers long before the advent of James Webb himself, and even prior to the creation of the first telescope that allowed humans to peer into the celestial abyss. Yet, there's a palpable anticipation, a hope, that with the launch of this revolutionary space observatory, answers to these age-old questions may become closer than ever before. New capabilities most accurately describe what the professional astronomical community expected from Webb, while new discoveries were what the broader space enthusiast community eagerly anticipated. Indeed, in just over 2 years of active operation, Webb has already uncovered numerous astonishing and previously unseen features. Its penetrating gaze has delved into the most hidden corners of the cosmos, revealing the secrets of exoplanet atmospheres, the internal structures of nebulae, complex interactions between galaxies, and the remnants of supernovae. However, perhaps its most revolutionary observations have been of the early universe, where astronomers sought to glimpse the very first structures into which matter coalesced. What they observed truly astonished many. In light of this, it is crucial to synthesize the most significant discoveries already made possible by the unprecedented sensitivity and resolving power of the James Webb Space Telescope. This article will primarily focus on the early universe, as unraveling its mysteries was the core mission of this new telescope. To begin, it's essential to understand what the James Webb Space Telescope Observatory truly is, and to briefly recall its key features. As of today, it stands as the largest and most powerful space telescope ever created by humanity. Before its triumphant launch on Christmas Day in 2021, it endured a long and arduous journey fraught with complexities, from the initial design and construction phases to significant budget overruns and numerous launch postponements. The majority of these challenges stem from the fact that many of the technologies required for its creation literally had to be invented from scratch. Webb is an infrared telescope, designed to observe radiation invisible to the human eye but exceptionally crucial in astronomy. This radiation possesses the unique ability to penetrate dense clouds of gas and dust, allowing us to peer into forming early galaxies, witness the birth of planets, and uncover hidden details within nebulae. Furthermore, infrared radiation is what visible and ultraviolet light from galaxies in the early, and thus ancient, universe transformed into. This is the light that, due to the expansion of space, gradually lost its energy until it finally reached our telescope mirrors as faint infrared signals. Since infrared radiation is thermal, the telescope's design engineers faced the necessity of developing methods to eliminate excess heat sources both within the telescope itself and in its surrounding environment. Any heat could interfere with observations and drown out the desired radiation from distant, faint sources. To prevent thermal contamination, Webb was equipped with a 5-layer sunshield, which effectively reflects radiation not only from our Sun but also from our own planet and its moon. The second Lagrange point of the Sun-Earth system was chosen as the home for the new telescope, a location maximally distant from our planet's thermal influence. Here, it does not orbit Earth, like its predecessor Hubble, but rather orbits the Sun, effectively accompanying our planet on its cosmic journey. Protected from external heat sources, the observatory's scientific instruments cooled to an incredibly low temperature of -233 degrees Celsius (-387 degrees Fahrenheit), with the coldest among them, Miri, being just 7 degrees Celsius (13 degrees Fahrenheit) warmer than absolute zero. This provides the observatory with unprecedented sensitivity to infrared signals, particularly those arriving from the very dawn of the universe. Thus, observing the early universe was undoubtedly the primary scientific justification for building such an expensive and revolutionary space telescope. This constitutes its core mission, and it is precisely this that should bring us closer to the answers to some of the questions printed on the observatory's homepage. Therefore, It is no surprise that during its first 2 years, the cosmic dawn was among Webb's main targets, drawing significant attention. The period within the first few 100 million years after the Big Bang is of immense interest to scientists, as it was then that matter ignited into the first stars, which, along with dust and gas, coalesced into the first galaxies. How those galaxies looked, and precisely when and how they formed, is what scientists aim to discover to understand how their properties change over time. The Hubble Space Telescope made groundbreaking observations, peering into the depths of the universe when it was approximately 500 million years old. In these early cosmic epochs, galaxies were discovered that differed significantly from the familiar spiral or elliptical forms. They were compact and lacked distinct, clear structures. Before 2022, Hubble held the impressive record for the most distant known galaxy, designated GNZ 11. The number 11 in its name indicates its significant redshift, which, in turn, corresponds to a universe age of approximately 400 million years after the Big Bang. It is more illustrative and accurate to express information about distant objects through the age of the universe to which a specific redshift corresponds, rather than through distance in light years. This is because the actual distance to such an object can reach tens of billions of light years. For example, for galaxy GNZ 11, this distance is about 32 billion light years. Such figures can mislead the public, who are aware of the finite speed of light and that the age of the universe itself does not exceed 14 billion years. This confusion is entirely understandable, as it implies that these galaxies were moving away from us faster than the speed of light. Indeed, this phenomenon does occur, and cosmic expansion can carry galaxies away from each other at speeds exceeding that of light. To avoid further misunderstandings, it is advisable not to use light years in the context of objects in the early universe. Instead, it is proposed to adopt a parameter like redshift. This indicator characterizes the degree of shift in an object's emission spectrum towards longer, i.e. redder, wavelengths. Since the expansion of the universe is the fundamental reason for the stretching of light waves from distant objects, redshift currently serves as the only correct and unambiguous method for estimating distance when referring to objects in the early universe. For convenience, each time a specific redshift value is mentioned, information about the corresponding age of the universe will be provided. Thus, with the commencement of full-scale scientific operations by the James Webb Space Telescope, Galaxy GNZ 11 lost its record holder status and currently holds only the 11th position in the ranking of the most distant objects. Accordingly, the top 10 are occupied by galaxies discovered by Webb as part of its early scientific programs. One such program, known as the JWST Advanced Deep Extragalactic Survey, JADES, already presented the world with new record holders in September 2022. An international team of scientists focused Webb's observations on a region of the sky made famous by the Hubble Space Telescope's renowned deep-field images. However, while Hubble required collecting light for over 20 days, Webb accomplished the same task in just 20 hours. The new observatory managed to identify hundreds of potential galaxies with redshifts greater than 10. And in October 2022, out of 250 candidates, researchers identified 4 objects whose spectroscopically confirmed redshift indeed exceeded a value of 10. Among them, Galaxy GSC 13, with a redshift of 13.2, became the new record holder, existing during a period when the universe's age was only 330 million years. In fact, this record did not last long, as a new, truly impressive distance milestone was set in 2024 within the same scientific program. In early 2023, scientists identified a very interesting object in the acquired data sets. Firstly, preliminary estimates of its redshift were somewhere in the range of 14, already vying for a new record. Secondly, it exhibited an unusual, even excessive brightness, which was too much for a galaxy in such an early universe. Not enough time had passed since the Big Bang for a galaxy to form capable of accumulating such a significant number of stars. Therefore, a dilemma arose: either the distance estimate to the object was incorrect, or existing models of galaxy formation required revision. Regarding distance estimates, astronomers indeed face certain methodological complexities here. In a simplified form, scientists take images of specific sky regions, for example, using the NIRCam instrument, which is equipped with a set of diverse filters. Each filter selectively transmits radiation only within a certain wavelength range, so the intensity of the source's light is perceived differently through each of them. Thus, astronomers measure the luminosity of galaxies through each filter, and compare these data with models of various redshifts. The model that best matches the acquired data allows for a hypothetical determination of a galaxy's belonging to a specific redshift value. This approach is called the photometric method, and it is the most productive way to estimate redshifts, as it allows for covering vast cosmic regions and simultaneously analyzing numerous sources. However, the problem is that this method cannot be considered absolutely accurate, as objects in space do not appear reddish solely due to cosmic expansion. They can naturally exhibit less blueness if they contain a predominant number of cool stars, or if there is a significant amount of dust formations absorbing part of the radiation. Consequently, two galaxies may have similar color characteristics when observed through filters, yet possess different redshift values. To be unequivocally certain of their conclusions, researchers are compelled to verify their estimates by resorting to a more precise method, spectroscopy. By decomposing light streams into their spectral components, they analyze characteristic absorption or emission lines inherent to specific chemical elements, such as hydrogen. Now, by comparing the degree of shift of these lines into the red region of the spectrum with reference values obtained in laboratory conditions, scientists can accurately determine the redshift value. Or ultimately, these galaxies could simply be oddballs, exceptions to the rule. They are bright, making them easier to detect in the early universe. But this doesn't mean they are representative of the galactic population at that time. We can draw a parallel to exoplanets. Initially, strange hot Jupiters were discovered, and only later, with improved observational capabilities, did it become clear they were not as common as once thought. The unexpected data from the Webb telescope, which initially caused surprise, now have not only hypothetical but also more robust explanations, which have been subjected to rigorous scientific scrutiny. In one published paper, researchers demonstrated that at least some of those unusually bright galaxies might have shone not due to an abundance of stars, but as a result of intense activity from a central black hole actively consuming surrounding matter. The friction of gas rapidly swirling in the accretion disk causes it to heat up and subsequently emit light and heat. This additional luminosity gives galaxies significantly greater brightness than what would be solely attributed to stellar emission. However, this explanation does not seem to apply to object GSC-14 and several other sources, which appear too massive for their brightness to be explained solely by black hole activity. Consequently, another scientific publication showed that stars and galaxies of the so-called cosmic dawn can indeed form through powerful, sudden bursts, a concept known as bursty star formation. This idea is not purely speculative. Astronomers regularly observe similar phenomena in the local universe, particularly often in galaxies with relatively low mass. While the precise reasons for this phenomenon remain debated, perhaps due to the comparatively small mass of these galaxies, supernova explosions are capable of expelling significant volumes of gas into the circumgalactic medium. This gas later returns, initiating a new cycle of star formation. The fact that this is not observed in larger, already formed galaxies is likely due to their significantly greater mass. Because of the increased gravity in such galaxies, supernovae cannot push gas beyond their boundaries, trapping it within. Ultimately, in massive structures like the Milky Way, stars are born at a relatively constant rate. Thus, those initially shocking galaxies don't necessarily have to be exceptionally massive. Their exceptional brightness might be a deceptive consequence of an enhanced luminosity effect caused by another wave of bursty star formation. The modeling conducted by the authors successfully reproduced the same number of bright galaxies observed by Webb, including both confirmed objects and extremely bright candidate galaxies. Therefore, if this hypothesis is correct, the James Webb Space Telescope might indeed have captured these young, actively shining galaxies at the most opportune moment in their evolution. However, it's also possible that the observed picture is the result of a complex combination of various astrophysical factors. Certainly, one cannot completely rule out the possibility that further, more extensive observations might indeed prompt scientists to revise certain aspects of their existing cosmological models. However, it is important to recognize that to justify such a radical change as shifting the date of the Big Bang, arguments significantly more substantial than just a few bright galaxies are required. The fundamental principle of the scientific method remains unwavering, and it was excellently formulated in Sagan's famous words. Extraordinary claims require extraordinary evidence. It is noteworthy that while some of the most distant galaxies pose difficulties in explaining their formation with modern theories, the larger structures into which these galaxies aggregate align quite well with those same theories. Another outstanding discovery made with the James Webb Telescope was the detection of a so-called baby galaxy cluster. Such massive formations, like galaxy clusters, naturally do not arise immediately in their mature form, as astronomers observe them in the relatively nearby cosmos. Instead, they must undergo a specific evolutionary path, including a protocluster stage. Therefore, to understand the mechanisms of galaxy cluster formation and growth, scientists need to see them in their embryonic state. As part of another early scientific program called Galaxies, the Webb telescope was aimed at a region of the sky containing the well-known Abell 2744 cluster, more widely known as Pandora's cluster. This location proved to be extremely fortunate for searching for extremely faint and distant objects because the immense gravity of this cluster creates a powerful gravitational lens, functioning like a giant magnifying glass. Even the most advanced infrared telescope benefits from the assistance of nature's own gravity to peer into the deepest corners of the universe. Astronomers were fortunate to discover 7 individual galaxies here, which, according to photometric data, exhibited identical redshift. This was subsequently definitively confirmed by spectroscopy. Each of these galaxies had a redshift of 7.88, indicating their existence in a universe that was only 650 million years old at that time. Given their relative proximity to each other, the region of space they occupy is approximately 20 times denser than the average matter density in that early universe. This is compelling evidence that these galaxies are unified in a cluster, the most distant one known to date. The precise determination of redshifts also allowed scientists to measure the velocity dispersion of these galaxies, i.e., their speed relative to each other. These measurements showed values within 1,000 kilometers per second, which undoubtedly indicates the enormous gravitational interactions securely holding these galaxies together. Thus, researchers were able to calculate the mass of the dark matter halo, which serves as an invisible scaffold for such large-scale structures. Based on their calculations, they modeled that the mass of the halo of this discovered protocluster in the modern epoch could be comparable to the mass of one of the largest known clusters in the universe, known as the Coma cluster. In other words, what now appears to us as a cluster of tiny red spots in the infant universe could have transformed over cosmic time into a colossal structure containing thousands of galaxies. This is now, quite possibly, one of the largest clusters in the entire universe. Thus, astronomers finally were not just speculating but actually observing one of the most crucial steps in the process of universe formation and growth. Astrophysicists have long been troubled by a fundamental problem that arose almost immediately after it became possible to observe the universe during its first billion years of existence. This enigma is directly related to the nature of black holes. Although the internal physics of these objects remains unusual and not fully understood, specialists have a sufficiently clear idea of their formation mechanisms. Primarily, they form as a result of the collapse of massive stellar cores at the final stages of their life cycle, or, for example, from the merger of 2 neutron stars. There is even a hypothesis suggesting that many black holes might have originated simultaneously with space at the moment of the Big Bang. But this explanation is considered somewhat exotic and extremely difficult to empirically prove. Nevertheless, a very curious aspect emerged. Prior to the launch of the James Webb Space Telescope, the earliest known black holes were extremely bright quasars observed at redshifts greater than 7. Most studied quasars were recorded with redshifts within 6. The few instances that were observed in the earlier universe turned out to be true oddities. The point is, they possessed astonishingly large masses, hundreds of millions or even a billion solar masses. Of course, this is not particularly surprising when considering galaxies around us. For example, the black hole at the center of M87 has a mass of about 3.5 billion suns, and Sagittarius A** at the heart of the Milky Way is 4 million times more massive than the Sun. However, in a universe that is only about 800 million years old, the existence of such black holes is perplexing. The issue is that, regardless of the amount of matter absorbed, black holes cannot grow at an arbitrarily high rate. There is a clearly defined limit to the rate of mass accretion, known as the Eddington limit. Thus, if one assumes that these ancient massive black holes collapsed from some star, even a star 200 times more massive than the Sun, they simply would not have had enough time to accumulate such a colossal mass in a few 100 million years. In other words, it is extremely difficult to explain their rapid growth other than by assuming they were already born thousands, even tens of thousands of times more massive than the Sun. But how then did they appear? It is unlikely that even the first generations of stars could have been that massive. This, in essence, is the unresolved problem that astrophysicists currently face. One of the most intriguing hypotheses explains this by suggesting that supermassive black holes can originate directly from collapsing gas clouds, essentially bypassing the stellar phase. At least, computer simulations on supercomputers demonstrate the possibility of black hole formation in precisely this way, immediately possessing significant masses. Ultimately, these objects would gradually absorb matter and, over hundreds of millions of years, could grow to sizes corresponding to those observed at redshifts around 7. However, to test this hypothesis, it would be extremely desirable to discover black holes in an even earlier universe, at higher redshift values, and determine their evolutionary stages. This is where James Webb played a key role. In 2023, a group of scientists, while observing a gravitational lens from Pandora's cluster, discovered a galaxy named UHC-1. The spectroscopically confirmed redshift of the object was slightly greater than 10, indicating observation of the universe at an age of only 470 million years. The galaxy itself is interesting due to its early nature. However, observing it for 2 weeks with another space telescope, Chandra, researchers detected intense X-ray emission. This is a characteristic signature of supermassive black holes, around which superheated, accelerated gas intensely emits radiation. And given its brightness and the energy released, the black hole's mass is estimated to be in the range of 10 to 100 million suns. Thus, this is another giant, too massive for such an early universe. Moreover, based on the brightness of the galaxy itself, astronomers estimated its mass also to be within 10 to 100 million suns. This means that the black hole's mass is comparable to its host galaxy. This fact starkly contrasts with black holes in the centers of relatively nearby galaxies, whose masses usually constitute only a fraction of a percent of the total mass of the host galaxy. Thus, the entire significant mass of the black hole, as well as the volume of X-ray emission it produces, combined with the brightness of the galaxy itself, discovered by Webb, all align very well with the hypothesis that black holes can originate from the collapse of gas clouds. One of the most distant black holes looks exactly as it was expected to appear under this hypothesis. Essentially, by observing this object, astronomers are seeing only a short stage of evolution for both the black hole and the galaxy itself, when their masses are still quite similar. However, in the future, the black hole will lag behind the galaxy, which will accumulate stellar mass more quickly. New stars are born faster than a black hole can grow. Therefore, as a result of this race, the galaxy may grow into something more familiar to our eyes, and its black hole will eventually constitute only a small fraction of its mass. Of course, it cannot yet be asserted that the mystery is fully unraveled, as more data are needed to form confident conclusions. But for now, the idea that black holes do not necessarily need stars for their birth may be very plausible, and perhaps such objects reside in the hearts of large galaxies. To delve into one of the significant scientific achievements made possible by the James Webb Space Telescope, it is necessary to first consider the observatory rightly regarded as its predecessor. One of the 3 key scientific justifications for creating the Hubble Space Telescope was its application for the most precise determination of a fundamental parameter, the universe's expansion rate. Before the Hubble era, ground-based observatories faced substantial uncertainty in this matter. Specifically, the age of the universe was estimated within a broad range of 10 to 20 billion years. Thanks to Hubble, astronomers managed to reduce this inaccuracy to just 1%. This was possible due to the telescope's ability to penetrate deeper into cosmic space and measure the brightness of certain types of variable stars known as Cepheids, as well as type Ia supernovae. The known luminosity of these cosmic objects allows for precise distance determination, while their redshift indicates the degree of cosmic expansion between them and our galaxy. Thus, these methods represent effective tools for determining the rate at which the universe pushes galaxies apart due to its expansion. However, there is a certain problem. The method based on Hubble's observations yields a universe expansion rate of 73 km per second per megaparsec, whereas high-precision measurements of the cosmic microwave background performed by the Planck satellite indicate a value of 67 km per second per megaparsec. The reasons for this discrepancy remain unknown, and this inconsistency has been dubbed the Hubble tension. It is important to note that the divergence in the results of these two methods emerged as early as the beginning of the 2000s and has only intensified over time. Initially, it was assumed that incorrect measurements might be the cause, and that over time, as accuracy improved, both values would eventually converge. However, this stubbornly has not happened. Consequently, astrophysicists, puzzling over this issue, are actively searching for any possible explanations, meticulously analyzing the smallest inaccuracies that could have influenced the observations. Since the reliability of Planck satellite data is virtually unquestioned, the primary efforts to find inaccuracies are focused on Hubble's observations. One potential problem is considered to be the determination of distances to Cepheid variable stars. It has been suggested that measurements of their brightness may become increasingly inaccurate as the distance to these stars increases. In other words, a systematic error may arise, causing increasing inaccuracy in measurements with distance. This phenomenon may be related to the fact that light from Cepheids blends with light from other neighboring stars. Indeed, this effect becomes more pronounced at greater distances, when crowded stars simply cannot be distinguished individually. Furthermore, the presence of dust in galaxies further complicates observations, as Hubble conducts its observations in the visible light range. However, the James Webb Space Telescope possesses the unique ability to penetrate dust without problems because it observes infrared wavelengths. Naturally, Webb also has significantly greater resolving power. Individual stars and its images appear much clearer, allowing for better depiction of Cepheids and eliminating any potential inaccuracies. In 2023, a group of scientists conducted a study of 5 galaxies containing 8 type Ia supernovae, as well as about 1,000 Cepheids. The data they obtained did not refute, but merely confirmed, the correctness of the data obtained by Hubble. It would seem that another potential source of error had been eliminated, but the Hubble tension still persists, as Webb confirmed the Cepheid distances. Nevertheless, this issue has not yet been definitively resolved. There are studies in which scientists use the Webb telescope to measure distances not only to Cepheids but also to other so-called standard candles, which include, for example, stars at the tip of the red giant branch and asymptotic giant branch stars. Notably, the average value obtained from red giant observations is significantly closer to the value provided by the Planck satellite, which, at first glance, could resolve the Hubble tension. But Cepheids do not show such agreement. Ideally, it is necessary to find galaxies in which several different types of standard candles are present, such as Cepheids, supernovae, red giants, and others. This allows for the calibration of obtained distance values using data from different sources. However, in practice, such galaxies are extremely rare, and it will take time before they are discovered. Thus, it is still too early to say whether James Webb will resolve the cosmological crisis or not. One can only confidently assert that it has opened up new possibilities that will help eliminate at least some of the possible inaccuracies in measuring the brightness of cosmic objects. Therefore, for cosmology, this telescope is a new, powerful tool, and its significance extends far beyond cosmology alone.